Do pause the video and make sure that you've understood this question fully, but reading through most of the information is on the diagram, but there are some coefficients of friction to acknowledge, so I'm just going to write those on the diagram here. So one between the two blocks and another one between block B and the floor, whatever the ground is. The tension we're also told is 5 newtons. So I'm just going to, so I've got a bit more space, I'm just going to take the relevant parts of that screen, and here we are. So looking at part A, show that the system remains at rest. Well, thinking about that, just try to imagine yourself pulling on block B like that. 5 newtons is not very much, so we're pulling block B, but not very hard. And the whole thing isn't moving. So since A and B are not moving relative to each other, there's no need to think of them as separate blocks. So I would consider the whole system as one in part A. So it's a 13 kilogram block, so 13G downwards and a normal reaction up, and we've got tension pulling to the right and some sort of friction stopping it from moving, pulling to the left. So I've just written fric there. Now, show that the system remains at rest. So in other words, if it remains at rest, friction, the F max must exceed 5. So we just need to calculate F max. Well, F max is mu r, and we know that mu is 0.3 and r is 13g, just by resolving vertically. And so multiplying those together, F max comes out to be 38.22, and then just to prove that that's bigger than 5, make sure you write that down and conclude that it remains at rest. So part B is a bit more complicated. You're told that the tension is now 100 newtons and the blocks are going to move relative to each other. So just imagine if you were to yank block B, block A would remain roughly where it is, but it might accelerate a tiny little bit towards you whilst it's in contact with B. So block B is going to have friction above and below, whereas block A is going to just have friction below. And actually block A is going to be accelerated by that friction. So we need to think very carefully and make sure you spend in an exam plenty of time over this part. Create force diagrams for the separate blocks, and make sure you include any equal and opposite forces. So here's my block A. We've got our vertical forces, nice and easy, so I'm just going to put 5g down and r up. We've got an F max pulling it to the right, and that's kind of it really. That's the force diagram for block A. And that F max is going to accelerate block A. You can see very clearly from that diagram it's imbalanced, so it will accelerate to the right. Now block B, it's got its 8g down, but I've drawn the r on. The r down there is the vertical r from A. These are equal and opposite forces. So block B is pushing up on block A, and block A is pushing down on block B with the same force, which is why I've got the same r here and here. Now, because I'm going to have reactions from on block B as well from the ground, I'm actually going to call this RA. You see I put a tiny little a there, and similarly in the other diagram here as well. Now, also F max is going to be equal and opposite, because this force here on A is caused by block B, and it's equal and opposite, so we'll get an equal force but pointing the other way, acting on block B, on the top of block B, from block A. So again, I'm going to call both of those the same thing in the diagrams. But again, there's going to be friction from the ground as well on block B, so I might call these F max A on both. Okay, right, so I've drawn on RB, which is the reaction on block B from the ground. And also the other horizontal forces acting on B, we've got the 100 newtons pulling it to the right, that's our tension, and I've got F max B, which is for the friction from the ground on block B. Now you might be wondering, these are now complete force diagrams, but you might be wondering, where are the equal and opposite forces for RB, for the 100, for the 8G here, and for F max B? Well, those exist, but we haven't drawn them because we haven't done a force diagram for the ground. And if we did that, it would look like this. Earth, you'd have F max B pulling it the other way, so the Earth is being pulled to the right by that friction. You've got the RB, that's the sort of kind of the weight of both blocks effectively pushing down on Earth. That makes sense. The 100, somehow that 100 is caused. Imagine if you were pulling on a rope to create that 100 Newton force here. Your feet would be pushing back on the Earth with 100 newtons the other way. And you'd have this 13G pushing up. The Earth is, of course, pushing up on the blocks. So let's get rid of that. We don't need those. Now, coming back to block A, resolving vertically, RA must equal 5G. And that allows us to work out F max A, which is mu times RA, which is 0.15 times 5G, which gives us that expression there, 3/4 G newtons. And that allows us to work out its acceleration using F equals ma. So we've got 3/4 G newtons, mass 5 kilograms, and that gives us A is 1.47 meters per second squared. It's a very similar process then for block B. Again, start by resolving vertically, and this time we get that RB is equal to RA plus the 8G weight acting on B. RA we know is 5G, so I've just replaced that. So 5G plus 8G gives us 13G. And then again we can work out F max B using our friction formula. Mu, that's the different mu this time, so it's the 0.3 times RB, which is 13G. So now we have 3.9G newtons. And then just do another F equals ma. This time the force is the resultant of all those horizontal forces. So we've got 100 pulling to the right and both of these frictions pulling back to the left. So I've done those as negative forces here, making up the resultant, equals mass times acceleration. We're only looking at block B, so don't do 13 kilograms. It's only block B, so it's only 8 kilograms we're interested in here, so 8A. And that solves very easily to give you the value of A as 6.8 meters per second.